In today's video, we'll learn about momentum and impulse. Momentum can be defined as an object of mass moving with a velocity. It is a product of its mass and velocity. So we see that the equation for momentum is equivalent to its mass times its velocity. We also see that momentum is a vector quantity. Therefore, we can have an x component and a y component when measuring our momentum. According to Newton's second law of momentum, we can calculate net force acting on an object by taking the change in an object's momentum divided by the ellipse time. This equation tells us that the changing an object's momentum requires the continuous application of a force over a period of time, with a constant force acting on an object over a time interval defines an impulse. So an impulse is equivalent to a constant force multiplied by a change in time. Impulse is also a vector quantity with the same direction as the constant force acting on that object. This brings us to the definition of an impulse. The impulse of the force acting on an object equals the change in momentum of that object. We can see that the change in momentum can either be calculated by a constant force applied over a time interval, or by taking the mass times our final velocity minus the mass times our initial velocity. The magnitude of the impulse delivered by a force during the time interval is equal to the area under the force versus time graph, or is equivalent to our change in momentum. So by taking the area underneath the graph, we can calculate the impulse or our change in our momentum. In our first example, it states that the force shown in the force versus time diagram acts on a 1.5 kilogram object. In part A, we're asked to find the impulse of the force. So we see that we have force versus time diagram, which we learned that the sum of the area underneath the curve will give us the impulse. So we can break our graph into a rectangle and a triangle and sum up the areas to find our impulse. So we see that the area of a rectangle is our base times our height, which will be 3 times 2, plus the sum of the area of the triangle, which is 1/2 the base, which is 2, times the height, which happens to be 2 as well. And this will equal our impulse. So when we calculate this, we'll see that our impulse is equal to 8 newtons per second. In part B, we're asked to find the final velocity of the object if it is initially at rest. So we know that impulse is equal to our change in momentum, and our change in momentum is equivalent to our mass times our final velocity minus our mass times our initial velocity. Since we know our impulse and the mass and our initial velocity is at rest, we can solve for our final velocity. So if we solve for our final velocity, we will get the equation where final velocity is equal to our impulse divided by our mass. And if we plug in the values that we are given, see that our final velocity is equal to our impulse, which we calculated to be 8 newtons per second, divided by our mass of 1.5 kilograms, which will give us a final velocity equal to 5.3 meters per second. Finally, in part C, we're asked, find the velocity of the object if it is initially moving along the x-axis with a velocity of -2 meters per second. So yet again, we know that our impulse is equal to our mass times our final velocity minus our mass times our initial velocity. And since we know our impulse, we know our mass, and our initial velocity is given to us, we can solve for our final velocity. If we rearrange the equation to get final velocity by itself, we'll get our initial velocity plus our impulse divided by our mass. If we plug in the values we're given, our initial velocity was said to be negative 2.0 meters per second plus our impulse of 8 newtons per second divided by our mass of 1.5 kilograms. And if we calculate this out, we'll see that our final velocity is approximately 3.3 meters per second. Our second example states that during a storm, rain comes straight down with a velocity of 15 meters per second and hits the roof of the car. The mass of rain per second that strikes the car roof is 0.0 kilograms per second. Assuming that the rain comes to rest upon striking the car, find the average force exerted by the rain on the roof. So if we summarize the information we're given, we have an initial velocity of negative 15 meters per second. We have the mass over seconds is equal to 0.060 kilograms per second. And our final velocity of the rain is 0 meters per second. And we're asked to find the average force exerted by the rain on the roof. So we know that impulse is equal to our average force times our change in time is also equal to our mass times our final velocity minus our mass times our initial velocity. So if we're trying to solve for the average force, we can divide each side by the change in time to get the average force by itself. Therefore, we'll have our mass times our final velocity minus the mass times our initial velocity divided by our change in time. And since our final velocity will be 0, this part of our equation will be equal to 0. Therefore, we'll be given an equation where negative mass times our initial velocity divided by the change in time will give us our average force. Our initial velocity is given to us, but our mass nor the time is given to us. However, we can simplify this equation into our mass divided by time times our initial velocity. And if we look over to the information we're given 0.060 kilograms per second. Has the same units as mass over time. So we can plug in our value for mass over time as 0.060 times our initial velocity of negative 15 meters per second. And if we calculate this, we'll get an average force that is equal to a positive 0.90 newtons.